In this video, I give the electrical details of the IRC station. Although not of interest to the average person, they're crucial to the operation. Enough information has been provided from a theoretical standpoint for the average person to understand what's going on.
This is a view of the interior of the powerhouse, taken circa 1893. Originally, the electrical power equipment consisted of three 200 kilowatt generators, manufactured by the Canadian General Electric of Thomson Houston design. TH had been incorporated into General Electric in 1892. This plan view shows their location on the powerhouse floor. The switchboard contains switches and circuit breakers used to control the electrical output of the station. This is the layout of the actual switchboard installed in this station. At the top of the diagram is the 600 volt supply that is connected to the trolley line. The circuit breaker, located at the top of the switchboard, is connected to the positive bus. The ammeter is next in line. It displays the current that its generator is producing. The voltmeter displays the output voltage of the generator to which it is connected, by means of the voltmeter plug being inserted in the appropriate voltmeter jacks. The operation of the equalizer connection is beyond the scope of our discussion. Suffice it to say that it is used to ensure the proper sharing of load between parallel generators. The equalizer switch is used to open the connection when a generator is not in operation. Two switches are shown in this arrangement because of the expectation that more generators will be added as line traffic expands. Eventually, there were 6 generators installed in the powerhouse. This disconnect switch allows the generator to be isolated from the 600 volt bus. The switch shown here has 3 blades. One of these was used to control power to the station lighting. The series field is named for the fact that it is connected in series with the generator armature. The series field rheostat is connected in parallel with the series field. We'll discuss the rheostat operation shortly. The shunt field is in parallel, also known as being in shunt with the motor armature. The shunt field rheostat is connected in series with the shunt field. Now let's look more closely at how the fields and the rheostats work to keep the generator's output voltage as constant as possible. The generator schematic has been redrawn in order to explain how it was intended to operate. In most DC generators, the armature is the rotating part. The current is transferred to the stationary part of the generator by means of brushes. The shunt field is connected in parallel with the armature. As a result, current flows in the shunt field whenever the generator is operating. This current sets up the generator's magnetic field. The series field is in series with the armature. It too causes a magnetic field, but of less strength than that of the shunt field. The output voltage, which results from the combination of the series and shunt fields, is connected to the panel bus and then to the trolley lines. One side is connected to the streetcar rails, and the other to the overhead conductor, commonly called the trolley wire. The shunt field supplies the major portion of the magnetic field. The armature turns in this field, and in cutting the lines of force, it generates the voltage that causes the current to flow to the trolley car's motors. The series field adds to the shunt field in proportion to the current being supplied by the generator's armature. As more cars go out on the line, or some cars climb a hill, the current drawn from the generator increases. This would normally result in a drop in generator voltage at the brushes, but since this current flows through the series field, it strengthens the total field. The more current drawn, the greater the strengthening of the field. This increased field brings the generated voltage back to normal. If the voltage were allowed to decrease, it would cause all the cars on the line to slow down. The field rheostat is a variable resistance. Moving the slider changes its resistance. Increasing the resistance would reduce the voltage produced by the generator, and vice versa. This rheostat is in parallel with the series field. If the resistance is reduced, then less current flows through the series field, and again the voltage output of the generator is reduced. These rheostats are used to tune up the operation of the generators so they work well together. However, this static adjustment is not enough to control the dynamic requirements of trolley cars operating on the line. This is accomplished by means of the voltage control section of the switchboard. In this photo, we see a typical 4-pole General Electric DC generator of the 1890s. The rotating part of the generator is the armature, shown here. Notice how its shape mimics that of the symbols used in the previous diagrams. The 4 field poles produce the generator's magnetic field. They are shown here surrounding the armature. On each of these poles is placed both the series and shunt fields. The commutator is attached to the armature and turns with it. The commutator is a mechanical rectifier that changes the alternating current in the armature into direct current to drive the trolleys. The brushes ride on the commutator and are the means by which current in the rotating armature is transferred to the stationary conductors, feeding the switchboard and the trolley line connected to it. The brush gear supports the brushes and allows them to be rotated, if needed, to reduce sparking. The drive belt transmits power from the prime mover to the generator. In our case, the prime mover is a hydraulic turbine with a drive belt above the powerhouse floor.